In this video, we'll be finding the oblique and the vertical asymptotes of this rational function, and then we'll give a rough sketch of the graph. A rational function will have either an oblique or horizontal asymptote, but it won't have both. If the degree of the numerator is one more than the degree of the denominator, in this case 3 and 2, then you can have a slant or oblique asymptote. We want to make sure that the rational function is in lowest terms. So we can go ahead and factor the numerator here. It's the sum of cubes. So this should factor into the sum of the cube roots, which would be x plus 1. And then the other factor will be the square of the first term of the binomial minus the product of the two terms, x and y. So this would just be x. And then plus the second term of that first factor squared, which is 1. The denominator factors into x minus 7, the trinomial, and x plus 2. So like I said, this one does not have a horizontal asymptote. If the degree of the numerator is less than the degree of the denominator, then you expect to have one horizontal asymptote. Now to find the vertical asymptotes, simply factor the denominator like I have here, and whatever values generate a 0 for the denominator, but not the numerator. Okay, any value that makes the numerator 0, any value that makes the denominator 0, but not the numerator, will give you a vertical asymptote. So the vertical asymptotes here, we can see that 7 will make the denominator 0 and negative 2 will make the denominator 0, but not the numerator. So the vertical asymptotes would correspond to x equal to 7 and x equal to negative 2. That's where the function is undefined. So you will never expect the graph to cross. The graph will never cross the vertical asymptotes because that's where it's undefined. Now the graph may cross the horizontal asymptotes or the slant asymptotes. Here we don't have any horizontal ones, so we get this. And it is in lowest terms. There's no factor that will divide out. So to find the oblique asymptote, we simply take the numerator and divide it. Here we use long division by the denominator. So this is going to be x squared minus 5x minus 14. And this is the way you find the oblique or slant asymptote. Set it up as a long division. So you want the numerator and descending powers. We have it. Same thing with the divisor. And then we go x squared into x cubed goes x. And then we multiply the x times the divisor. So this should be an x cubed here. X times x squared is x cubed. Plus the next one, minus 5x times x is a minus 5x squared. This should be a minus 5. X squared. And minus 14 times x. So minus 14x. And then we subtract. So x cubed, subtract x cubed gives me 0. And here I don't have a x squared term with the first entries here, so it's going to be 0 subtract the minus 5x squared. This gives me a positive 5x squared. And then 0 minus the minus 14 gives me a plus 14x. And here is 1 subtract 0, so it just leaves me a 1. And you continue the division until the degree of the remainder is less than the degree of the divisor. Here it's a 2 and a 2, so divide by x squared. 5x squared divided by x squared is a plus 5. Then multiply by 5 times the divisor, so 5 times x squared is 5 x squared. Then 5 times a minus 5x is a minus 25 x. And then 5 times a minus 14 is a minus 70. And then we're going to subtract. So it's 14x, subtract minus 25, that becomes a plus 25x. So this gives me 39 x. And then 1 minus a minus 70 makes it a plus 70, so this is going to be 71. So basically then, what we have here is that this x cubed plus 1 divided by x squared minus 5x is actually equal to the dividend x plus 5 plus the remainder, which is 39 x plus 71 divided by the divisor, which is x squared minus 5x minus 14. Now for the slant asymptote and for the horizontal asymptote, we want to know, what does the function approach as the x value gets real large or real small? So you can see here that for this is the remainder. So as the x value gets real large, the denominator gets real large, much larger than the numerator. So basically this is going to go to 0. So as x is real large or real small, the function f, I'm going to call it y, f of x or y, same thing, is approaching x plus 5. So y is equal to x plus 5 is the equation of the oblique asymptote. We have the vertical asymptotes, x equals 7, x equals negative 7, so we can plot those in the graph. We can plot the graph of the oblique, and then look at what the graph approaches, or how the graph looks like, by plotting some information here. So you can see now, we want to find out a couple of things that will help us with the graph. Without using the graphing calculator. So you can see that if x is equal to 0, we replace the x by 0 here. We get, on the numerator, we get 0 cubed is 0 plus 1. That's 1. And the denominator, x squared is 0 minus 5 and 0. That cancels out. It gives you minus 14. So the point 0 and negative 1 over 14. That's your y-intercept. That's where the graph crosses the y-axis. Now, for the x-intercept, we want to know, okay, what's the value of x when y is 0? So if this is 0, then this part, the fractional part over here on this side, is going to be 0 when x is what number? Well, you can see right here, when x is negative 1 and 1 is 0. So when y is 0, the function then will be 0 at negative 1. So this is your y-intercept. And this is your x-intercept of the graph. Again, if you have your function in lowest terms, the values that make the denominator 0, but not the numerator, would generate the equations of the vertical asymptotes. In this case, 7 and negative 2. X equals 7, x equals negative 2 are your vertical asymptotes. Now, if the degree of the numerator is less than the degree of the denominator, y equals 0 will always be a horizontal asymptote. And there's other options for that. But right now we're just focusing on oblique and vertical asymptotes. Now, one technique that you can use to sketch the graph of a rational function without using the graphing calculator is to find the values where the denominator is 0. We have those, 7 and negative 2. Where the numerator is 0, and that's a negative 1. And plot those values on a number line. Now, overview of the finding the oblique asymptote. To find the oblique asymptote, if it has 1, and it's going to have 1 if the degree of the numerator is 1 more than the degree of the denominator. Divide, long division, divide, and then once you get to the remainder, that is when you can't divide it anymore, and that means that the degree of the divisor is less than the degree of the remainder. In this case, 39x plus 71 is the remainder. Degree 1, divisor has degree 2, so we stop. Basically, you can go through this process here, but all you really have to do is just reject this, discard this, and take the y instead of equal to x plus 5. So over here then, we have the summary. We clear this. Here's the information we have. So vertical asymptote, x equals negative 2, x equals 7. The slant asymptote, or the oblique asymptote, is y equal to x plus 5. Y-intercept is 0 and negative 1 over 14. And the x-intercept is negative 1 and 0. So on the number line, I have plotted points at negative 2 and 7, corresponding to the vertical asymptotes and the value that makes the numerator zeros. So again, those just come from values that make the numerator or the denominator 0. And then what I do, the next thing I do, I want to know where the graph is. Well, let me look at this over here. So on this graph here, have the coordinate system. This line right here corresponds to x equals 7. This one over here on the left vertical line corresponds to x equals negative 2. Those are the vertical asymptotes. So I have a vertical asymptote there. Vertical asymptote there. And the oblique or slant asymptote is this line right here. So I plotted 2 points for that line. 0 and 5 would be right there. Negative 5 and 0 would be over here. So then all I do then is pick a value in each of these intervals. So I pick a number to the right of 7 and plug it into the function, the rational function, and determine the sign. What do we get? Doesn't matter what number you pick to the right of 7. You can pick 8, 7.5, 9. Over here it's plus. And then pick a number between negative 1 and 7. Doesn't matter which one you pick. You can pick, the easiest one would be 0. And what value do we get? So negative 1 would say be there. Negative 1, 0 corresponds to your x-intercept. So in here, it's a negative. Plug it into your function. Then pick a number between negative 1 and negative 2. Say negative 1.5. Plug it into your function. In here, the value of the function is positive. Then to the left of negative 2, and that end, we'll pick any number there. I want to make it easy to pick a number close to negative 2, say negative 3, plug it into the function. And right here it's negative. And that's normally what you would expect with a typical rational function. The signs will alternate. But sometimes when you have a square somewhere in there, it's not going to be the case. But here goes plus, minus, plus, minus. So let me look to the right of 7. Notice the graph doesn't cross the x-axis over here on this side. The only place it crosses the x-axis is at this point right here, -1, 0. So without even plotting any points, I could have something that looks like this. The graph could, you want the graph to approach the slant and the vertical. So I could have something that goes like this over here, but there's no intercept there. So this would suggest, and you can verify this by plugging in some actual points to the right of 7, plug in 7, plug in 8, 8.5, whatever. The graph should go something like this. The portion looks like that. Now between -1 and 7, the graph is below the x-axis because it's a negative sign, and it crosses the x-axis at -1, 0, this point right there, and it crosses the y-axis at barely below there, -1/14. That's pretty small. So let me just do it this way. It's gonna go like this, and then it's gonna come down and approach vertical asymptote x equal to 7. Now between -1 and -2, that's this area right here, I have a plus. So that tells me the graph has to go up. So it's going to go up. The problem here, I have a slant asymptote there and a vertical. So I want it to approach either one or the other or both. But in this case, if it goes back, if it approaches it this way, it has to cross the y-axis. But I don't have another y-intercept. Keep in mind that the graph will never cross the vertical asymptote because it's undefined at those points. But it can cross the horizontal if you have one, or it can cross the slant or oblique asymptote if you have one. So the only way this is going to go up like this and approach, get closer and closer to that vertical asymptote. Now to the left of -2, you look at the number line over here, I have a negative. So it tells me the graph has to be below the x-axis. And I have a slant and a vertical. So this would suggest that I have something that looks like this. And that's what the graph looks like. Now I want to point out to you that if you enter this function, this rational function on your graphing calculator, and you start graphing it, you might not get this portion up here. Because your window for that graph might be too small, so you might only see this part right here. So one third of the, or 2/3 of the graph. So if you want to see it all, you might use your zoom, or you might make the window. Okay, if you go to the window for the calculator, for the x, the standard range for the x for the standard graph would be x from -10 to 10, y from -10 to 10. So you might have to increase the y from -10 to say 30 something, or the x from -10 or so to 30 plus something. So you have to play around with it. But this is kind of what the graph is going to look like. Thanks for watching. We'll see you next time.